Math 1343, week 11, video 4, post-ANOVA analysis, testing the difference in two population means. Believe it or not, this is the final video in this series. Noticeably shorter series than in week 10. So before we do this, let's summarize what we've done so far in this ongoing example about ATM usage. So far we've done the following. Number one, highlight these things as we talk about them. We've estimated the mean usage of ATM 3. We did that by creating an interval for its mean. And since that interval did not contain the sample means for ATM 1 and ATM 2, we concluded that ATM 3's mean usage was different than ATM 1 and ATM 2. Next, which we did in video 3, we estimated the difference in mean usage for ATM 1 and ATM 2. Since that interval contained 0, we concluded it was possible the two ATMs had the same mean usage. Or equivalently, we did not have enough evidence to conclude that their usage was different. And that's actually the better conclusion, that we lack the evidence to say this, therefore we're going to say the other thing instead. But we haven't really compared ATM 2 and 3. Well, we sort of did in the first interval. When we did the interval for the third ATM, and it did not include the second ATM sample mean. So we kind of did, excuse me, we kind of did. I'm so sorry. Might be bronchitis, I'm not sure, or allergies. That's probably it. I know it's not COVID. But what about ATM 2 and ATM 3? We have some evidence based on the first interval that they had different usage, but maybe we actually better test the two against each other. So our third and final post-ANOVA analysis process, if you will, is going to be testing the difference in two population means, which again, we've done already when we reviewed some statistics 1 material in this class. But this one is post-ANOVA, meaning that we're going to use the results from the ANOVA to pull off this hypothesis test. So how do we do this? Well, let's do it using the critical value approach. And if you don't mind, I just want to draw a red line underneath what it is we're doing. Because, whoa, not sure what happened there. There we go. All right, testing the difference in two population means post-ANOVA, critical value approach. It's the same as before, just have to make adjustments where necessary. Number one is to state the hypotheses. And when you're testing the difference in two things, the hypotheses are normally the difference is 0 or it's not, which is equivalent to saying that the two means are equal or they're not. And then we'll find the critical value. But to find the critical value, we have to know the distribution to use. In this case, it's going to be the t distribution. And because it's the t distribution, we're going to need to know the degrees of freedom. Well, looky there. It's the same degrees of freedom as before. So in all of our post-ANOVA analysis inferences, estimating one population mean, estimating the difference in two population means, and testing the difference in two population means, the degrees of freedom is always the same. I'm going to jump back into the text box just for a second and say that this is the DF errors from the ANOVA table. All right, and then we have to calculate the test statistic, but to do that, we need a formula. Well, the formula for the test statistic is pretty much the same as it was back in Stats 1, or in the review at the beginning of the semester. We start by calculating the difference in the two sample means, so x bar I minus x bar j. And then we divide that by some, excuse me, that's not a standard error. Oops, come back everything. Let's just undo this real quick. It's not the formula for the standard error, it's the formula for the test statistic, which in this case is t, because we need a test statistic to compare to the critical value. Since critical value is a t, the test statistic is a t also. But we calculate this one, we don't look it up. The numerator of the fraction is the difference in the sample means, so x bar I minus x bar j, well, over the standard error. So what's the formula for the standard error? Well, that's where the standard error is the exact same standard error that we used when we estimated the difference in two population means, which was long tall square root MSE times the sum of the reciprocals of the sample sizes, Ni and Nj. So we got to do that calculation again. And then we make our decision. Then, of course, answer any question that was asked. If we were using the p-value approach, just a reminder, we would skip step 2. We don't need a critical value. We would do we would skip step 2, then we would calculate the test statistic, find the area of the tail or tails cut off by the test statistic. That would give us the p-value, which we would compare to the significance level. So it's business as usual with a slight modification in the critical value because the formula for degrees of freedom changed, and a slight modification in the calculation of the test statistic, specifically the formula for the standard error. All right, so let's pull this off. We're going to test the difference in means for ATM 2 and ATM 3. Notice I did not give a significance level, and do you remember what that means? The default significance level is always 5%, so when it comes time to use the significance level, we're going to assume it's 5%. All right, so let's start with the hypothesis. Since we are testing the difference in the means for the second ATM and the third ATM, we'll say that our null hypothesis is mu2 is equal to mu3. Notice that this is the same as mu2 minus mu3 is equal to 0. This is why it's called testing the difference in means. Actually, we're comparing if two means are equal. The alternative would be, no, they're different, meaning that they're not equal to each other. I do want to remind you that the hypotheses are always about a population, so no X bars here. This is equivalent to saying mu2 minus mu3 is not equal to 0. All right, so there's our first step. That was pretty easy. Our second step is to calculate the critical value, which means we need to draw a picture. Here's the curve. And even though I didn't state it, I'm going to go up here and write use alpha equals 5%. But again, in the absence of a clearly stated significance level, you assume it's 5%. All right, so where does that 5% go? Left tail or right tail? Trick question. It's two-tail test. Because the alternative hypothesis contains not equal to, this is a two-tail test. So we still have to make that observation. Two-tail test. All right, so we cut off two tails. And the significance level represents the area of the tails. So in this case, because our significance level was 5%, each tail is 2.5%. So we will have two critical values. We'll look up the one on the right because our T-chart has right tail areas. The one on the left will be its negative by symmetry. We also need degrees of freedom. Just a reminder that the degrees of freedom is the EF errors in the ANOVA table. It's also N minus K. If we just go back and check that out real quick, let me get rid of all this highlighting. The N is the grand sample size, so it's the sum of those eighths, which is 24. The K is the number of groups or number of samples or number of populations. In this case, there are 3 ATMs, so K is equal to 3. So N minus K equals 24 minus 3, which is 21. Or we could just look at MS errors because that's equal to N minus K. All right, so it's still 21, but I wanted to go through it one more time just because I want this video to be self-contained and not just say, remember from the previous video? All right, so our degrees of freedom was 21. And now it's Z-chart time. We have 21 degrees of freedom. We have 2.5% on the right tail. Let's go to a Z-chart. I know I've got one here somewhere. Chart, where are you? There you are. Okay, so where were we? 21 degrees of freedom, 2.5% in the right tail. Didn't we look? I think we looked at one up in one of the previous videos. Yep, 2.5%, which is this column here. 21 degrees of freedom. 2.0796. 2.0796. 2.0796. And because it's a two-tail test, we have 2.0796 there. To complete the picture, we should label that the middle is the non-rejection region, and the tails are our rejection regions. All right, so business as usual, and it's time for step 3. Step 3 is to calculate the test statistic, and in order to calculate that, we start with the standard error. Standard error, which is the square root of MSE times the sum of the reciprocals of the sample sizes, and since we're talking second and third populations, it's N2 and N3. Our MSE comes from our ANOVA table, so let's go back and look at that. MS errors is right here, 138.7143, and our N2 and N3 are the second and third sample sizes, but they're both 8. So MSE is 138.7143. 138.7143. Each of the sample sizes was 8, so we have 1 over 8 twice. This goes into a calculator, comes out to 4 decimal places because it's obnoxious. This will be the same standard error that we had in the previous video because the sample sizes were the same. It was 5.8889. Now that we have our standard error, we can say, so our test statistic is the difference in our sample means divided by that standard error. Now remember, we're testing mu2 and mu3, more specifically mu2 minus mu3, whether or not it's 0. So we need x bar 2 minus x bar 3. Let's go find our x bars. X bar 2 minus x bar 3. That would be these two right here. I don't like that color. I know that's kind of irrelevant, but that's fine. All right, so we're going to do second minus third, so 34 minus 49.25. 34 minus 49.25. 34 minus 49.25. At 34.00 if you want to go for significant digits. All right, so let's see what this equals. Again, I would recommend putting this in your calculator. As simple as it is, there are people that mess it up. At 4 decimal places, I got negative 2.5896. But I'll do it again just to make sure. I'd rather do it twice, get the same answer both times, than do it once and get it wrong. If you do it once and get it wrong, you really won't know. But I got the same answer, negative 2.5896. All right, so all the dirty work is done. Let's highlight the important stuff. We've got our test statistic, negative 2.5896. We've got our critical values, and now we're ready to make our decision. I'll draw this on the next page, but our test statistic is going to land to the right of the greater critical value, so it will land in a rejection region. So step 4. Again, just redrawing. Our critical values were plus or minus 2.0796. 2.0796 here, negative 2.0796 here. Our critical value, those were our critical values. Our test statistic was negative 2.5896. Negative 2.5896 lands over here. Negative 2.5896. And so our decision, since we landed in a rejection region, our decision is going to be to reject the null hypothesis. So what can we say? We reject null and accept alternative. We're not really accepting it. We're just saying that evidence suggests that it's the one we're going to go with. I guess you could say we accept it, but it's our best guess, if you will. Thus, we conclude, what do we conclude in context? We conclude that ATM2 and ATM3 have different mean usage, which is what our confidence interval in the first and second video suggested, since the interval for the third population mean excluded the sample mean from the second population. All right, before I wrap up this video, I want to quickly remind you how to do this using the p-value approach. And I'm not just doing it to give you more to use. Some of you are going to use statistics in future classes, sociology, psychology, economics, physics and engineering possibly. So your professor might say, yeah, we do the p-value approach, I don't do the other thing. So I would be remiss if I didn't go over the p-value approach real quick. And it won't take very long. The key thing to remember about the p-value is that it is the area of the tail or tails cut off by the test statistic. In this case, our test statistic was negative 2.5896. So if we want to look at the p-value approach, we need to get this to draw. Sorry, I'm bouncing all the time, but when I tap my laptop, the screen does this and the camera moves. But if we want to do the p-value approach, we need to start by taking our test statistic and cutting off the tail. Our test statistic was negative 2.5896. But be careful, the p-value is not this area. I know p-value is area of the tail cut off of the test statistic, but do you know why it's not just that area? Remember what type of test this was? Based on the alternative hypothesis, this was a two-tail test. So the significance level represents the area of two tails. In this case, they were 2.5% each for a total of 5%. So if we're going to compare the p-value to the significance level, the p-value has to come from the same number of tails. So how do we do that? It's actually pretty easy. We just cut off a right tail using the opposite sign of the test statistic. So 2.5896. So the p-value will equal the area of these tails. Because of symmetry, we really only need to find the area of one of them, and then we can double it. But we're doing a t distribution. These are t's. And remember that our degrees of freedom was 21. Using the t chart to calculate an area is not efficient because, as I'll remind you by going back to our t chart for a second, most t charts can only accommodate a small number of different areas. So the chance of landing on one of those areas is very slim. It's virtually zero, but let's not go into that. So what can we do? We can come up with a bound for the area of that tail by looking in the correct row based on the degrees of freedom and finding the t values that serve as boundaries for our test statistic. So what does all that mean? All that means is that we're going to go to the 21st row and we're going to find the t values that 2.5896 is in between. So let's do that. 2.5896. 1 second, folks. 2.5896. I just wrote it on the dry erase board so that I would not have to go back and see what it is. All right, so let's go back here. And we want to come up with bounds for our p-value. So first, let's go to the 21st row, because that was determined by our degrees of freedom. And ideally, you would hope to look across and find our test statistic, which was 2.5896, at least the positive version of it. But 2.5896 is not in here. So you find the two numbers that's in between. 2.5896 is between these two numbers. Zoom in on that. In the 21st row, 2.5896 is between 2.5176 and 2.8314. Since our test statistic lands between these two t values, that means the area of the tail cut off by the test statistic lands between these two areas. So the best thing we can say about the right tail is that its area is more than 0.5%, but less than 1%. Let's write that down. We know that the right tail area is more than 0.5%, but less than 1%, based on our t-chart. So what does that mean about our p-value? Well, our p-value is the area of both tails, but the tails are the same. So all we have to do to get the p-value is multiply everything by 2. And if we multiply everything by 2, that means that our p-value, because it was a two-tailed test, is between, if I double 0.5%, I get 1%, and if I double 1%, I get 2%. So without technology, the best that we can say from our t-chart is that the p-value for this hypothesis test is between 1% and 2%. Does that allow us to make a decision? Of course it does, because our significance level was 5%. It wasn't given to us, but I think I did write it down. Yeah, but even if I didn't give it, we would still assume 5%. We know our p-value is between 1% and 2%, and more importantly, it's less than 2%. So now we can wrap this up, p-value style. Since the p-value less than 2%, it must also be less than 5%, the significance level. Thus, what do we do when the p-value is too small? We reject the null hypothesis, just like we did in the critical value approach. But like I said, if you use statistics in future classes, you may be told, nah, p-value approach, forget critical value approach. So I wanted to remind you how to find the p-value. And I'm glad it was this one, because when it's a two-tailed test, you have to remember that the p-value is twice the area cut off by one of the tails, so that you can have two tails to compare to the two tails represented by the significance level. And that actually wraps up this series of videos. Keep an eye out for the homework.